Hi, Tobias. Thank you very
Hi,
much.
how are you doing? How are you
Fine,
doing?
fine. Ah, it is tough a little bit.
You're welcome. Maybe you'll just give them a few minutes for more people to log in because I
Yeah,
see
yeah.
now it's 21. Then after that, you can just proceed after
Sure.
a few minutes. Welcome.
Thanks. We are running to the finishing line, isn't it?
Yes, we are in the last lap.
Yeah. Yeah,
by
it was.
tomorrow, by tomorrow we'll be seeing the finishing line at the horizon.
Yeah. still some people are coming. Let us wait quite a bit.
Okay.
Because today is a very important day as far as the classes we have covered in the, I think.
Okay, then we can give them more time. No problem.
Yeah,
okay.
A little bit, yes.
No worries.
I have a problem in my Ubuntu. Can I share my screen until the other come?
Yes, Muna, you can do that.
Thank you. Become like this, no response. This morning was working, but now like this, I don't.
Okay.
I don't.
Yes, this is sometimes happens for me also when I am using. You are using virtual, isn't it?
Yeah. Yes, it is.
Okay. What you do is you just now you cannot close, but make a hard close, a hard shutdown. That means you the power button. So close your computer totally.
Okay, restart or shut down?
Restart.
Restart, eh?
Shut down.
Okay.
Shut down everything and restart. Yeah.
Okay. Okay. Thank you, bro.
You are welcome. And yesterday, I think still some people are tuning in. That is very good. Today, as I have told, you have started this course with some introductory aspects, including the theory and some practices and things like that. And all this boils down what we do as a breeders is towards the finishing line, to the final analysis. Our ultimate aim is to select, to identify and select best genetic merit animals for the users. So in the last couple of weeks, you have come across long way. You have covered several topics in this regard, including theory, practice, and things like that. And during this time, you have managed to do some exercise on theories. You were able to estimate variance components. You were able to build a mixed model equations and also estimate genetic merit of animals, fixed defect solution, and things like that. But what is next? What do we do with these solutions we have? What do we do with these variance components we have estimated? So today, I will try to give you a bit of a flavor of how can we make sense of what we have done so far. So this is why this is important today. We don't talk very much, but what we talk is very important because from the practical aspects, because some of the things that what we will discuss today may not be, or you may not find them in the textbooks. It is just from the practice. So that is why it is very important that we talk today about these things. But before we go directly to that one, I would like to remind you all that a couple of several minutes ago, I have forwarded an email containing a lot of materials for you. And these all materials are helpful for you today. So I advise you all to download these files from your emails and put them in somewhere in the directory. And then we'll come to that one by one. How do we use them? What are they for? And what do they mean? But before going directly into this one, I want to do some housekeeping things regarding. Yesterday, Jonas had started something. Jonas, are you with us? Okay, it doesn't.
Yeah, Doctor.
Jonas.
I am.
Okay. Have you managed to run relax to still? Because you have done everything right, and the last step was to just get the pedigree file there, or to download the pedigree file.
Yeah, no problem. I have discussed with my friend. I will manage it.
Okay. Okay, yeah. Very good.
Okay.
Okay, the other thing, share screen. Have I shared my screen? No, okay. So the other thing which we have discussed yesterday, especially estimating variance components.
Hello, sir.
Hello?
Hello, sir.
Yes?
It's Abdul from Niger.
Yes, Abdul. Go ahead.
Yeah, please, I want to know if after the end of this training session, the canvas will have access on canvas or not.
I can ask that one if Tobias, Dr. Keno is with us. He is the right person to answer that.
Okay.
Dr. Keno. I can ask him quickly.
Okay, thank you, sir.
It is supported, hosted by the Egerton University, and they are the ones who know about this thing. I will ask for you just quickly.
Thank you.
Okay, welcome. time. Okay. Just hold. Okay. Can you see my slides?
Yes.
Yes,
Yes.
we can, bro.
Oh, okay. Let's start. Muna, did you manage to get your computer running now?
Yes, bro. Thank
Okay.
you.
Welcome. Yesterday, as you remember, we started estimating variance components for a bivariate model, 2 traits, and we managed to do the estimation of parameters. But in DMU, as you might all know, we get the variance component solutions, and especially if you have a multi-trait model, a 2 traits, 3 traits, 4, 5 traits, then in those cases, it is the user's responsibility to post-process the estimated variance components. That means you take the variance component solutions, the 2x2 or 3x3. If you have 5 traits, 5x5 variance covariance components for genetic permanent environment, for residual, and you have to make your own estimates of genetic parameters like heritability, repeatability, genetic and phenotypic correlations. So for doing that, one of the help is coming from using Octave. Octave allows us to write scripts to do mathematical computations. So in this case, I gave you a very small script that can calculate, that can read the 2 variance covariance component from the bivariate model and estimate for you genetic parameters like heritability of the 2 traits you analyzed, the phenotypic and genetic correlations. So this is this one. So yesterday I forgot to tell you, because although if you write a small script, you can create a script file. The way you can create a script file is you just type wherever you are in the directory, you write touch calculate parameter, a kind of .m. And one thing that you should remember is that Octave script files are always having an extension or suffix m, .m. That means the Octave program understands it. By doing this, you create a file called calculate parameter.m. Then you can just copy, simply block this part, copy and paste into this file you have created. You can open it by Joe, this one, and then you paste it in. So if you want to run that file, you can just Octave lesson sign, put the Octave script file, then the output will be written into a file called parlog. Because I am showing you this, you can use this script to do, if you have 5x5 traits, you can just make it longer and add some parameters and things like that. Otherwise, it is can be adapted for for another problem also. If you have another problem analyzing, for example, instead of 2 traits, maybe 4 or 5 traits also, you can use it. Okay, I think I have it somewhere here. Yes, here. For example, if you see in this, in my screen here, I have this script written. Once you copy this one from the email, you just open, first touch and then create this file. This this command will create you a file called that one. So you open that one. First, you copy the script from the email, then you open that one and you paste it in. I did exactly like that one, so I have pasted it in. So in the script, there are some things because I have calculated here heritability, but also there is a possibility that you save that file, that heritability into a file. So if I say, for example, save heritability, here what I'm telling is to Octave to save this part which I calculated as a heritability under the name file name heritability and take this value. So immediately Octave, what it does for you is it will take the output from this calculation, and write it out into a file for you. And when you go out and when you run, you get a file called heritability here. It is here written. So if you open, you can see clearly here there are two values. The first one is the heritability for the meal kill, and the next one is the heritability for body weight. So the same also with genetic correlation and phenotypic correlation. And I am giving you this because you can adapt it in case you have much larger problems involving 5, 10 traits, 5, 6 traits, so you can adapt it that way. Okay. If you have questions on this one, you are most welcome. Before we go to other things. Okay. One thing which we have not covered while discussing about DMU is have you downloaded now all the things, the documents I have sent to you several minutes ago? Do you need some time to download them? Can somebody shout?
We have downloaded.
Okay, thanks. Do you need some time? Who needs some time to download the files? It's important that we go together through them. Okay, it looks that everybody is set. Have it. So one of the, I closed that one, I think. Let's close this one. So okay, we are done. So the next one is not that one. Yeah. I shared. Oh. Okay. Do you see my screen now?
Yes.
Yes.
Oh, okay. In this one, because if you remember, we're discussing about DMU. I have told you that DMU is a very versatile program that allows you to do not only estimation of variance components, also you can predict breeding values and also genomic enhanced breeding values. So we have seen how we estimate variance component, especially how we build the directive files for estimation of variance components. But here in this one, I can just simply, how simple it is to build on the directive file which you have built for variance component estimation. You can just, by adding few lines or by changing numbers, you can use it to estimate also breeding values. If you remember, if in one of the notes that I sent to you this morning, there is estimation of breeding values using DMU5. For this one, you just need only the directive file which we have used yesterday or the day before yesterday for estimating univariate or single trait milk yield model variance components for milk yield fitting a single trait model. In that one, if you just copy that one to somewhere and make few changes or 2-3 places changes, you just have the directive file for estimation of breeding values. So for example, in this example, what I'm going to do is I use the single trait variance component estimation directive file, which we have built yesterday or the day before yesterday, and change a few things, and I used it to estimate breeding values for milk yield for the animals. I have the same data, I have the same pedigree, and I have estimated variance components, so I have the starting values. So one thing that is very important to know is if you are estimating variance components, providing starting values is optional. By default, DMU provides an identity matrix. But if you are estimating breeding value, it is a must that you have to provide starting values. So in this case, we are lucky because we have already estimated variance components, parameters for this trait, we can provide that one. And if you don't have estimated parameters or variance components, you can also use some estimates from literature or from previous work and things like that. Okay, here as you can see, this, what I did was I just, if you want to do this exercise, you can just, while I'm doing this, you can exactly cut this part or copy this part and paste it somewhere in your directories, and you have already the directive file for estimating breeding values, and change the paths for the data where you have your data and the paths for pedigree. And the only thing you have to change is you have to tell DMU on the third line, on the third row, what kind of analysis you are doing. So if you look your manuals, it is clearly written. So in this case, we are estimating, if you remember, when we are estimating the variance components, the method we used was 1, that is variance component estimation. But in this case, it is 12. That means it is DMU5 for estimation of breeding values. The second one was the algorithm or the solver that we use is, it is conjugate gradient. In this case, there are 3 or 4 options you can check in your manual. So we use the second one from that one. But if you remember from our variance component estimation directive file, the number here was, in the second place was 1. That means AI REM algorithm. So the other things are the same. You are using the same data. We are using the same model. But lastly, there are few things that we have to provide. One is, as I have told you, a starting value we have to provide. If you don't have, if you don't have, or if you have not yet estimated starting values of variance components for this trait, you can get some numbers from the literature or something. Then you have to say here dollar and DMU5. Then you have to tell how many rounds of iterations to go, and convergence criteria, the solution will be converging at this converging criteria, and you give them the total rounds of iteration. That means it iterates every time until the convergence is reached. So even if convergence is not reached, that the run will stop at 3,000 rounds of iteration, and it will write out solutions for you. That is the breeding values for the animals, or all animals in your pedigree. So how do we run? We know how to run DMU for variance component estimation, and how do we run then? How do we run DMU5 for estimation of breeding value? It is exactly the same as you can see here. Always using any other DMU model, you have to start with DMU1. It is a data processing, a data step that that reads your data, checks your data, pedigree, sets up the mixed model equations, and finally outputs also the description of your data and things for quality check. And the solver step is run as DMU5, and you write the to log2. So in this case, all the intermediate process iteration and things will be directed to log2. Is that clear? If you can do it yourself or you can follow, I can quickly show you what you do and what you get from that one. What I did was here, I just copied this part. Just copied this part because I have the same data, the same pedigree. I copied this one and put it in my, I have already made a file called by touch, GMD. When I do this, this immediately creates for me a file called, a directive file called blub-dmu5 here. So I have done that already. I have also copied this part from my email. Now the second thing I do is I just open this one and paste it there. So I pasted it already there. So as you can see, I have changed this one from 1 to 12. I have made this one 2. And I went down because I am using the same model. I have provided a parameter file that is the genetic variance and the residual variance. This is a single trait, so we don't have covariances and things. So it is just 2 parameters we have to provide. That is the genetic variance and the residual variance. And I have to write this one, DMU5, the rounds of iteration and the convergence criteria. I can show you quickly what my parameter looks like. I have sent you a file called par also. So the parameter is looking like this.
Recording in progress.
one, it should be like this, I think. Okay, let us start and run it and see what we get. And then I do. And then goes on. This one like this, okay. Okay, here it gives the description of the data. 3,000 observations, average meal killed is this much. Log 1 control KU. Okay. Let us see now. Okay. Here is we are using the same model like we use for variance component estimation. So genetic variance is 9.6 and residual variance is 6.7. Total phenotypic variance is this much. As I have told you, this data is not a very good data, just the numbers are not biological reasonable, but for you to just understand how it is working. Okay, this part is fine. So once you are happy with the with the data, with the description of the data, with the files, the pedigree, and right, the second step is to run DMU5, and the way you run it is like DMU AI. So in this case, log 2, and we start the run. So it is done. It writes a lot of files for you. So in this case, when you run variance component test, you look for a file called par out. It writes out par out file. That contains your parameter files, which variance covariance components that you have estimated. But in this case, when you run breeding values using DMU5, you get a file called sol. This sol file contains all the solutions for fixed effects and also for random effects. So if you see your manual, there is a very nice description of what are the outputs of DMU5 and how they are read. So for example, I can just quickly open, but you have to check your it looks like this. I should begin from the, if you have regression equations, first you will get regression solutions here. And the second column tells about trait numbers. There is one trait. And the third number tells about random effects. In this case, the first part until I think 3, until 3 are fixed effects. These are fixed effects for the different fixed effect solutions. So you know which fixed effect solution to which are by this fourth column. It is telling which fixed effect you have. And when you go down the first column, when I think it is 4. This all 4 includes your breeding values. These all below breeding values, here are the ID number of your animals, and the eighth column is containing your estimates of breeding value solutions, and the last one is their standard errors. So you can just, by using a small program, if you want only breeding values, estimates of breeding values, you extract everything from here to the end. Control K. These are all breeding value for the animals, and here are the animal IDs. So it is a very handy program to use. You can run multiple trades and everything. All the solutions, fixed and random effects, are written into the sol file. So the sol file descriptions, the different columns, the different rows, what does it mean, is clearly indicated in the directive file. Okay, this is in brief just how you can estimate breeding values with DMU. It is a simple example using a single trait model, but you can also build up into multi-trait or bivariate model and things like that. And the way that you can use solutions or the way you run is more or less the same. Okay, any questions or?
Could I quickly just look at your directive file, the one for this run? I just want to see the bottom bit for the price.
You can just copy from the email. I just need the same. I can. You want to see on the terminal or the one in the transparency? They are the same.
On the terminal. On the terminal, because I think you included something on milk parameters. So
yeah, okay.
Okay.
So okay, I'll show you. I think this para file, milk par, I have sent it by email. If you don't have, I can put it just on the on the chat, and you can just copy and paste.
Okay. No, I wanted to see the code. The milk.par, you've already sent it to us. I have it. I just want the code because this code is not on the transparent, on the transparent document.
Is that so?
Yeah.
How come? This part?
Yes.
It's not there.
You've only included from prior start.value, then DMU5, 3000, then the 0 point something, then 3000 below. But then where we're including milk.par is not there.
Okay. You have, okay, this is a parameter file. And what you can do is you can just copy this one in the chat and save it to a file called milk.par. And put it there. But you have to put this file where you are running the runs.
Okay.
Okay. While you are trying to work on this one, let us see the files that I have sent you today. We start with, let me take out of this. Okay. I sent lecture on. No, not this one. Okay. Somebody had just asked me whether the files in the canvas made available even after the end of the course. Who asked this? Who was he? Do you remember? Was it?
We also have the same question, Doctor. We also
okay. So I have got the answer now immediately. This kindly Tobias has answered this one. So the files in the canvas will be available after the end of the course, after the course ended tomorrow. My advice to you all would be to download all the files and whatever materials there as soon as possible, because after some time it is anyway access will be stopped. So, but it will be available for some time. You can take your time, but download and get prepared, because those materials are very good materials that you get.
That's great.
That's great, sir.
Oh,
okay, thank you, sir.
Yeah.
Thank you for this great favor as well.
Welcome. So I will be happy to hear if somebody managed to run DMU breeding value runs. And let me know if you have a problem. Also, you can take it and try it whenever you have some free time. Okay. So the next thing which we are going to do is the most important part, that, as I've told at the beginning, that we have done a lot of things: estimated breeding values, estimated variance components, and a lot of things. And at the end of the day, we have to make sense of out of all these numbers. What we have got is just a bunch of numbers. For the farmers or for the users, they don't at all make sense. But there should be, as a breeders, we have to make these numbers make sense and meaningful, and they can be used, and therefore they can be used as a help to assist our farmers in breeding dairy animals, chicken or goats or sheep. So today we'll see that one. For that one to show you, what I need is just, you have done all these various runs during different weeks. Raphael, you have done reliability estimates using using APAX 99. You have also run a single trait repeatability animal model for the same data which I have used, using the same pedigree. Now what we are today doing is we just read those solutions, those reliability you have estimated, those breeding value solutions you have estimated, and combine them together and make a sense out of how we can identify top bulls and cows for selection, and to extend or to advise our farmers which bulls and which cows to use. For this one, I have provided a file called From GEBVs to Indices and Ranking of Top Bulls and Cows. I have a lecture, not a presentation, that I will start with that one, but first I would like you to download all the materials that I have provided to you. So it is clearly indicated in this document which I have sent by email. If you open one of the email files, you read that it says from GEBVs to indices ranking of top bulls and cows on their genetic merit for milk yield. So it says in this exercise we practice three things in their order below. So the first thing that we're doing will be that we estimate breeding values. You have already estimated, you have a solution somewhere, but I will estimate and show you. So you can also do it again if you want to. Estimate breeding values for milk yield feeding a single trait repeatability animal model using a Mix99i program, Mix99 program. For this, I have provided a parameter, milk para. It is in your email. You have to download or copy in the directory you have. And also, I have attached a clean file called animal model clean. And the second one is we estimate the reliability of EBVs using APAX 99. For this one, I have also attached APAX instruction, a file called APAX instruction, and also a clean file for estimating or for the Mix9i part of the reliability estimation. Usually, the data step of the reliability estimation is a bit lighter than the breeding values. On the third one, we standardize the breeding value solutions that we have got into indices with a mean 100 and standard deviation of 10 index points. This is the way we standardize to make them, they are the same numbers, but to make them sense for the farmers when they see it. Which animal is better than the others? How do I know? Then we combine the indices and their corresponding reliabilities.
You're not sharing your screen.
Sorry?
You're not sharing your screen.
Oh, very sorry, very sorry. This is, thank you very much for reminding this. How about now?
Yes, yes, it's on now.
Thank you. Okay, what I'll do is I'll go quickly above again and start. So you have a file this kind. Have you got this one?
Yes.
The reason, one thing, because you have already got the email, so I hope that you have opened it. But anyway, this is the file that I'm looking at. So in this order, we do estimate breeding values using animal model. I think you have done this with Raphael. So I have provided you also today the directive file for Mix99 and also the milk para file. The second one is we estimate reliability using APAX program. For this one, I have also provided you a file called indices.tar.gz. It is a compressed file. In those ones, all these files are there. The third one, we standardize a breeding value solution you get into indices with a mean 100 and standard deviation of 10 index points. And for this one, we use R program. That's why last time I told you to download R. So I have also enclosed R program to do this. So this is a very nice exercise. Once you use this, you can just upscale this one when you have 3 or 5 traits. So you can start with this one. So in general, note that I'm using the same data I have sent you before and the same pedigree we have sent you before. So how do you do this? To do this, it is the first step is just make directory somewhere in your home or somewhere, make their animal model, animod. It is this here where we are running the animal model breeding value solutions. Or if you have already estimated with parameter, just identify you have the solutions there. Make another directory called rel, so for reliability estimation. This is where we use APAX 99 to estimate reliability. And make index, make dir directory index. So in this one, we standardize this breeding value solution to indices. And in our exercise, once we do that one, finally our objective is to select or to rank the last or the best top 20 bulls and cows. So have you get a file called I have quickly show you, I think. Do you see my screen now? A file called indices.gz. This file.
Yeah, it is in the email. Yeah.
Yes. You have to uncompress this file somewhere. Okay, this is it with this one. Stop sharing this one. Okay. Okay, I will give you. I would like to know if you have got or downloaded this file. I think I shared this one. It is indices star. Make it bigger. It is this file.
We couldn't see your screen, Prof.
Oh, just hold on. I did. I hope now you see it.
Yes, sir.
Did you get this file from email?
Now it's okay. Yeah.
Okay.
Yes.
So get this file to your Linux. And the next thing what you have to do is to uncompress this file. From your Linux lectures, you know how to uncompress this one, -xvf. Then you just write the name of the file. So I will give you some 10 minutes because it's important that you get these files in your directory somewhere in your home or somewhere, and you should make those animal mode, rel, and other directories before we proceed on the lecture from GEBVs to indices and ranking. So I will give you some 10, 50 minutes break, and we'll get together after 50 minutes.
May I consult you on the
Sure.
previous one?
Go ahead.
I've been trying to run it, but I can't seem to
Okay.
get anywhere.
I stop mine, and can you share your screen and we see it together?
Just a moment.
Did you find something?
Just a moment. I have to log into.
Okay.
Yeah, log into Zoom from my laptop so that I share my screen.
Me? Hi, Sophie.
Hi. You can
you
hear
hear me? Yes, I
Yes.
can hear you.
Okay, so
do you have the? Can you go out? Go out of this.
Stop sharing.
No. Out of the Control C and out of this file.
Okay.
Yeah. ls minus lrt. Yeah. Okay. Copy that file from the chat, the one I sent you in the chat. Do you have access to that one?
I'm just trying to.
Okay, I can't tell you. Just hold on. Oh. You can write it if I tell you.
Okay.
Right. Touch. What was the name? Start val. It was a start val. You can write capital S. Yeah. Right. You are. Yeah. Okay. Underscore val. Capital VAL. Yeah. Okay. Now hit enter. Okay. Open this file. Start val. Hit the tab button, it will complete for you. Okay. Now write 1 space 1 space 1 space 9.6. Okay. 2 1 space 1. Okay. 6.7. 3. Now go on. 1 1 6.4. Okay. Enter. Control KD. Control C. Okay. Open now your directive file.
Directive file. Okay.
Yeah. Yes. Yeah. Okay. Start. Okay. Go to this start val and change it to underscore.
Okay.
Underscore and very good. Okay. Everything looks fine. Yes. Okay. Save it. Save this one. Okay. Start with DMU1. Yeah. Hit enter. Okay. It has done for you.
Yeah.
Okay. Yep. Yes.
Yeah.
You have the submission file there. Everything is fine.
Yeah. Thank you. I've seen where the issue was. I assumed when you just put start.value, it will bring in the identity matrix you were talking about.
Yeah, okay. In DMU breeding value estimation, it is a must. You have to provide the starting values.
Okay. Thank you.
Okay. Let us take 10 minutes break and we meet at 10 to what time was it? 10 to 2 to 3.
You are muted, Prof. We are not hearing you. Prof, you are muted. We are not hearing you.
I don't think if he has started. Are you able to hear me?
Hello, Ermias.
Yeah, I'm hearing you.
We are on break.
Yeah, I think the prof suggests we have, I think, a 10 minutes break. This is why he's still muted.
Okay, thank you.
Okay.
So we can't hear you.
Hello, Prof. We cannot hear you.
Yes, he is coming. He muted his microphone because we have a few break of 5-10 minutes.
But I see him doing something on the screen.
Yeah, he is trying something with his terminal, but he will come back as soon as possible. Okay.
Sorry, can you hear me?
Yes.
Yes, now we can.
Yes.
Yeah, I made my microphone off and I start talking. He's talking with us now. No. Okay, we have to correct the parameters. I think let's start with this part. So if you have downloaded the file, this indices star GZ, then what you have to do is just star minus XVF and the file name indices star GZ. If you enter this uncompress all the files contained into that one, there are, I think, 4 or 5 files that we are using in this next step. Okay, make it a little bit bigger. Okay. This is it. Oh, this is fine. So I have a few words, just introductory statements, what we are going to do, and I have a couple of slides about this one. Starting, as I have told, as I have indicated at the beginning of this class, that what we all have done in the last couple of days will be boiled down, come down to this aspect where we identify animals, rank animals, and publish proofs for use by the animal breeders. So regarding that, what are the different ways available? Just based on a single trait and a simple, but later on, since you have already a class on selection theory, you can combine different traits together and do that one. So my introductory statement in this regard is dealing from GEBV solutions. It can be genomic evaluation. In this case, you have GEBVs. If it is a pedigree evaluation, based evaluation, conventional evaluation, in that case, you have breeding values. In both cases, you are welcome to use this one to identify your animals based on high genetic merit animals to rank them and use them. So in this case, when we estimate breeding values, as you can see from the numbers I have given you, they are coming bunch of numbers. They don't make sense unless you know what you are doing. And we have to put them in some kind of meaningful way for the users. But before that, in Africa, we are endowed with a very beautiful nature that the weather, everything is very nice and beautiful. But it's also sometimes a challenge for animal breeders because we have to correct for every environmental effect. For if you want to estimate the genetic merit, one of the most important thing is to disentangle between what is genetic due to genetics from what is due to environment. So this is sometimes challenging because of the various environmental effects like the heat, the disease prevalence, and all other things are affecting also the performance of the animals, the performance of the organism. So from our theory that a performance of an organism, any organism, be it a plant or animal, has two main components, that is the genetic, the environmental, and the covariance between the two. So in this one, we get the phenotypic variance, also that is a sum of the genetic variance plus the environmental variance. But in this case, the beauty of, or the most important thing for animal breeders is using, we don't see the genetic effects. The only thing we can do is using performance data to disentangle to what is likely be due to genetic from that of what is likely to be environmental effects. So we have very diverse animal genetic resources. And once we are able to disentangle these two different components, then we can accurately estimate breeding values, the genetic merit of the animal. So in some cases, if you have a very good model, then you have incorrect breeding values, and that would mean that you are going to select the wrong animal for, and it is not a good thing to do. So estimated breeding values, as you might all know, provide a measure of the breeding potential of the animal for a specific trait. So if you are doing a single trait, and nowadays selection has never been on a single trait, it's a combination of traits. But for our understanding, we start from simple case and go to. So in estimating breeding values, we take into account performance data collected on relatives, and we also consider the relationship between the performance traits in case you have several traits in the breeding group, and the degree to which the traits are inherited. This is where the estimation of variance component comes. So the higher heritability that the trait has, and the faster the progress can be made by selection. So sometimes we are happen to work also in traits of low heritability. But whatever low heritability be, it is always possible to make progress. The best example of this is here in Scandinavian countries. They are known in the world for breeding animals for functional traits. These functional traits are very lowly heritable, heritability of 2%, 1% or something. But because they have started long ago, in 1980s, 70s, you can see the effect now. They are able to breed animals that are not only productive, but also disease resistant and with good fertility. We don't see that kind of downward trend when we see milk yield is going upward, because our main emphasis is on milk yield. So that has affected in most other countries that the fertility and functional traits went down. The trend goes down. But here they are able, at least, if not increasing, they have increased sometimes, but also they maintain it from falling down, fertility and disease resistance. So these information are combined together to give us what we call it is breeding values, pedigree valuation, also genomic breeding values. So as you know from, I have presented this slide that work for breeders, especially for those in evaluations, in national evaluations, and also those students who are, it's composed of a certain different tasks. This involves you having a raw pedigree, raw data, you pedigree prune, you validate your data, things like that. Then you combine pedigree information. In some cases, we are faced with missing parents in the pedigree. In those cases, you can construct, build phantom parent groups or genetic groups. I think it's a little bit out of this course, but sometimes maybe in the next course we can cover that one. Once you have various components, which you have done some couple of days ago, you set up a model, you have done already a couple of days ago, you have prepared your directive file instructions, and the next step is solving the model. You have solved the model. Now you have got your breeding value solutions, your GEBVs. Then what do we do? What comes after that one? So if we get breeding, if we estimate, sometimes we assume that once we are able to estimate breeding values and predict genomic breeding values or GEBVs or breeding values from pedigree evaluation, then that is not the end of the day. That is not the last thing for us. The journey has just started now. So you got the solution, you get the numbers, but there is a step one. We need to validate whether the thing is the solution, this bunch of numbers that we see when we open. I have shown you the solutions. There are a lot of numbers there. Are they making sense? Is the fixed effect solutions are right? Is the herds with high management are better than the low management herds? The age groups are animals with low, dairy animals with younger age producing more than the older ones. We need to check this all and make sure that the fixed effects are properly collected, environmental effects are properly corrected, and also the genetic effects. And this is the time that our main work starts after you estimate breeding variance components. You set up your model, you solve your BLAP equations, you get breeding values. But now you just stop and go back and see, do they make sense? So in this case, there are certain things that we should do before making use of whatever solutions you have estimated. They are just a bunch of numbers. The first thing is we need to check if the fixed effect solutions are reasonable. Do they make sense? Are the age effects right? The herd effect is reasonable. Do the lactation curves right one? Are they too flat? Are they too steep? Is there a reason for that? Do they vary? And you have to plot from this solution. I think in the next course we will show you how we fit different hierarchical effects and how to plot these curves from the solutions that we get. And you should see, are these seasonal curves within age groups, are they right for the lactation curve? And also, not only looking fixed effect solution, but also you should see the random effect solutions. That is looking at the distribution of breeding values. And from your course in BLAP and selection index, you know that BLAP assumes that estimated breeding values have a normal distribution. So if we plot what breeding values you have estimated, we should get a normal distributed curve like this one. So make sure it is not skewed or things like that. Is the means of EBVs and GEBVs by birth year of the animals are right? Do they make sense? is a breeding value solutions, the standard deviation of EBVs by bulls and cows, do they make sense? And in addition to that, also check the standard deviation of EBVs by birth year and by bulls and by cows. And the whole objective here is to make sure to see if there is something out of the ordinary, extreme variability. And there is also a need to check the stability of your evaluation, especially if you are working in national animal genetic evaluations. You are in AI stations or something. You are doing evaluation from year after year. New data is coming next year. Things may have changed. But remember that for bulls with large number of daughters, their breeding value is not easily changed. So if there is from 1 year to the other year, if there is large deviation in the breeding value in the indices for that bull, then you have to raise a flag and look back and see what is going on. And in general, evaluation should be stable. There is from time to time, from 1 year to another year. Of course, it varies in 5 years or 4 years time. It depends how much new data, how much new daughters are coming to the data. But very large, you should watch out for very large and extreme variability and difference. So whenever possible, also there are certain validation tests. For example, interval 1, interval 3 tests. Those tests, if you do them, they could easily identify, indicate how your evaluation is. It a good one, or is there some things to suspect? If there are things, for example, you can see just by plotting the genetic trend of the animals, if you get a trend like this one, what we can see with these sharp curves and things like that, if you see, in one of the cases, we have got a genetic trend for bulls like this one. And when we go and check the data, what we found was there was only 2 bulls in this year class. So and those kind of things, so you can combine these bulls or this year class with the others and things like that. You can solve those kind of problems. So in case things have not gone well, if your validation shows you something, the thing is you have to go back to the drawing board again. You improve where the problems were. Improve your model, and then you solve your model again. Again, you do validation tests. If it is passed, or if you find it acceptable and reasonable, then you have passed. It is very nice. Then you start to use those solutions to make them meaningful for the users. That is standardization and making indices. And after that, you publish to the users. So in this one, I can quickly show you another slide. I will come back to this one. Yeah. Yeah, this one. Can you see my screen?
No.
No. Okay.
No.
How about now?
Yes. Yes.
Yeah, we can see it.
Yes.
Yes. This is a snapshot of the Ethiopian routine national evaluation. So once from now 2019, once you get your breeding value solutions, there are a bunch of numbers. Then we have to convert them, and these are the things that we present to the farmers. They see the birth year of the bulls, the breed of the bull, the herd, number of progeny he has, the indices. That is what we standardize. Instead of saying this bull is 1.2 kilogram above the average or negative 2 kilogram from the average of the population, we can standardize it by making mean 100, and then we can also publish the reliability of that estimate to show how reliable, how much confidence we have on those estimates. These are the things that we are going to see now. Okay. So the thing is, in the solutions, like before we have opened in our this one, was it this one? I think yes. Do I have solutions? Yes. So these are solutions. In this one, you can see, for example, this is the solution that we get from DMU. Here is the ID of the animal, and this one is his breeding value for milk yield. Then we can see this is a very poor animal. It's below the average. It's negative. So these numbers, if you give to the farmers, what do they make out of this? They don't understand them very well. But if we standardize them to a certain value, for example, say the mean is 100, anything below 100 is less than the average of the population, anything above that one is above average of the population, indicates superiority. So this is a very good presentation. For this one, we look at using EBVs for selection of breeding candidates. In this one, we do standardization of EBVs, GEBVs into relative breeding values. And standardization is widely used after you estimate breeding values, and it is used in different ways in different countries. For example, in countries like Canada and Germany, they standardize the mean to 100 and the standard deviation to 12 standard deviation points. And relative breeding value is the genetic prediction that it has been standardized to a certain scale. That we take the mean of the breeding value for the population and we say it is 100. So depending on the genetic standard deviation, then we multiply that by 10 and say if it is 10 standard deviation, if it is 1 standard deviation, then it is 10 index points. If the animal is very highly productive and it is 2 standard deviation, then it is 20 points above 100 and things like that. So by standardization, we also make that EBVs and GEBVs are comparable, directly comparable across traits. For example, if you look the milk yield of the animal or the fertility, so if it is standardized to a mean 100 and things, you can see, oh, is he in milk yield above 100? So is he in fertility also above 100 or below 100? So you can easily compare across traits. So how do we standardize our breeding values? It's a very simple process. First, you run evaluation. Now, in this case, you have run your evaluation, you go to your GEBVs, and then you run your reliability runs, also feeding up packs, and then you prepare your pedigree, and because from pedigree you need to take the gender of the animals, whether it is bull or cow. And fourth, you standardize. So in standardization, then the equation is this one. That is the EBV of the animal for that trait minus the mean EBV of the population divided by the genetic standard deviation. The genetic standard deviation, you can take the square root of the genetic variance from variance component estimation for that trait. For example, if you estimate from in variance components, the genetic variance for milk yield, if you square that one, they took the square root of that, that is the genetic standard deviation. In some cases, they use the standard deviation of the estimated breeding values. Also they use, but in this case, we can use the genetic standard deviation as the square root of the genetic variance for that trait times 10 plus 100. So when you do this, you get the breeding values are standardized to a mean 100 and a standard deviation of 10 index points. So in this case, animals with high value with values above 100 are the best animals, and those below 100 are not below the average. Their performance is below the average of them. If you have traits like where minus is negative is required, like fertility, cupping interval, it should be lower. Somatic cell count, it should be low. In those cases, we multiply it by -1 so that it can be comparable to the others. But don't worry about this one. So how to construct the index is the formula is down there, you can see. So the standardization, standardized breeding value. The index is EBV of the animal minus the average of the all animals in the group divided by the genetic standard deviation times 10 plus 100. So this is in a single trait case. But in some cases, you may have a single trait and you have 3 lactations, for example. So in those cases, you can combine them together by giving them weights. For example, if your farmers are interested only in later lactation cows in the second and third lactations, in those cases, you can give more weight to the second, the third lactation, or they give more weight to the third lactation and next highest weight to the second. Then you can multiply the indices or the breeding values by these weights, and you will get the overall index for that animal. So always, as I've indicated, that selection has never been for a single trait. It has always been for a combination of traits. Number of traits is combined together. Breeders select for different traits. In those cases, we combine them into selection indexes. I think you have already your selection index theory course, and I will just go and show you how in a single trait case you can standardize your breeding value or GEBVs into a meaningful and useful, as I have shown, like the Ethiopian dairy cattle routine evaluation, where you can see here they have standardized them with a mean 100, and those animals with more than 100 are top ones and ranked here. And as you can see, the reliability also very high because they have a lot of information. Reliability is a confidence we have on the estimated breeding value, and this reliability is dependent on the information that went into the estimation of that breeding. The higher or the larger the information you have to estimate, the more confidence you have in that breeding value. That is the reliability is high. Okay, this much is so. If you have all the files together, then if you have questions, I take a few questions and then I will show you how we make sense out of all these things we have estimated so far and come up to a value that allows us to rank animals in terms of their performance. Okay. Okay, so if you have your files open and if everything is clear, then we go on how to do those things. So I have indicated, I have here, this is also the one that I have advised you to do. All the files I have sent to you for use. First, make 3 directors. One is for running. Also, it is if you are working in a AI station or breeding value or genetic evaluation, you need to have somewhere where you make your breeding value estimation runs, where the other one where you estimate reliability, and the other one where you make indices. So in this case, what I did was I have animal model. So here I have a repeatability animal model running to estimate breeding value for the animals. And the data I used exactly the data I have shared with you and the pedigree I shared with you. And the second one is I estimate the reliability for those animals using fitting that model. And finally, I have a directory with indices where I make the indices. So first, let us go to, if you have all the data you have received, then you can copy the animal model claim and something to that animal model directory. Animal model directory. Here I go to the animal model directory. Here I have the directory. In this one, I just run the animal model run, because here I run, I can show you quickly, I run a repeatability animal model, single trait animal model. I have the effects, age covariables, beam, calving year, season, lactation, herd, permanent effect, permanent environment effect, and genetic effect animal. So I have the data which I have sent you on the 1st of March, that is test data one. Also, I use the pedigree which I have sent to you, and I'm also using the pedigree file that I have sent to you now in the email. Here, my Mix 99 run. I think with Raphael, you have done already this. So here I described my data file very well. Then I describe my model here. Anything with hash sign is comment out, that is not read by your program. So it looks everything nice. Now I run my Mix 99. I run Mix 99. Animal model claim. So this is a quick run. It is done. What do I get? Let us look into log I. It is the file that is written out. Okay, Control KU. This is the data processing step. It describes the command we gave. It describes the traits, the model, and also shows you the data you have read. In some cases, you may read by mistake a different data. It makes also the effects and the model here, the fixed effects and random effects like DMU. Then it also describes the parameters that you are using. It's actually what parameters we have given. Then it gives you descriptive statistics of the data, the trait you are analyzing, milk, the number of observations you have, the mean and standard deviation, and the minimum and the maximum. And also it gives you descriptions of the covariables or regressions if you have. Okay. So this is in general the next. And the next step is to run Mix the solver. It is run like this, Mix 99S. So this is the step where we get breeding value solutions. So it is a small data. It's a quick run because I have a very fast machine, because I am working on a connected to the server. I am using the terminal. So our server is very fast, but in your case, if you run on your desktop, it may take maybe 5 minutes or 10 minutes, could be half an hour, depending how big memory the computer has. So now we have done Mix 99. We estimated our breeding value. Our breeding value solutions are in the file called SolAni. Solution of the animal, or the animal effect solutions. These are. So the first column is the animal ID. The second column is the number of descendants the animal has. And the third column is the number of observations that animal has. For example, if the first animal is a bull, he may have 2 or 3 daughters, but in the number of observation column, the third one maybe it can be 0 because he has no his own observations. So the last one is the breeding value estimate. As you can see for milk yield, that is negative. That means it is below the population average. It is poor animal compared to those like 1.2 or 3.2. Those indicates very good animals. So this is solely the solution that we use to make our indices and things like that. More, so we can see more. Some samples are very good. Okay. Now, if you have estimated, you have done the first part of the thing, and the second part is we have to estimate the accuracy, because estimating breeding values is not only the end game. We have to know what confidence, what level of confidence we have, how reliable are these estimates. For that one, we have to estimate the reliability by using APAX. So here we have, I have provided you also the APAX Mix 99 starting solutions, because we use a simplified model for reliability estimate. I used a slightly different model. Then I have APAX instruction for running APAX. This one. It's a little bit cryptic, but you can start experience with this one. Here, we estimate reliability. The first step is to run Mix 99i. In this case, our directive file is this one. So we direct it to logi. So it is quick, it is done. So it is exactly like the ones we had, where it reads the data, describes your model, gives you a data description, statistics, and that's all. And at the end, okay, you see it is done. When it is done, it is done. Now you are ready to start your APAX instructions. APAX. And the way you run APAX is you have APAX 99 program provided to you. Then within this minus less than and greater sign, you give the APAX instruction. Then you can write out the solution to APAX log. When you run that one, you get a file called PAVANI. So this is the file that contains the reliability for the animals. So for each animal, there is this one. If you go down the reliability, the first column is the animal ID. The second column is the number of descendants. For example, if it is a bull, the number of daughters or sons he has. And the third column is the number of observations, and the fourth column is the reliability estimates. If it is a cow, for example, the first column shows the cow ID, the second column shows the number of daughters or sons she has, and the third column shows the number of observations she has, and the fourth column shows the reliability values. So we have now estimated for each of the animals their breeding values and their reliabilities. Now the second and the last step, finally, how can we make sense out of this bunch of numbers? And we go to indices. And for this one, what we'll do is we read the breeding values, the Solanis, and also the reliabilities together and combine them, create the indices like with those standardization formulas, and build the proofs for the animals. And we rank them also using this program. For example, in this case, I have provided you the R script called make standardized indices R. I can quickly open this one. You can also quickly open make this one control KU. This is an R script which I have written for a small problem, like single thread case. We have also, I don't know, maybe we may not have that much time to cover for multi-thread case. I don't know if we have time. That one we can do that if you have time. But in the simple case, I can quickly go through this one and show you what it does. So before running this program, I think I advise you also to download this R script to your place, to your Linux. So I have written this some time ago. I don't know if I remember all what I have done, but I remember some of the things. What I have done here at the beginning is I am reading, you can see here, I am reading the Solani file where I estimating the breeding value of the animals. So I read those breeding value solution. I know they have 4 columns. The first one, the animal ID, and the second one, the number of descendants. The third one is the number of observation, and the last one is the breeding value estimate. And I make a table out of that one, animal ID, and 4 columns. I say animal ID and 4 columns. It has 4 columns, so it reads them there. I do a quick plot of the breeding values. So it should give me, as I've shown you, a normal distribution. If it is not normal, if it is too skewed or something, I should go back and there is something seriously wrong, because in BLOP the assumption is it's normal distribution. Okay, then I calculate the standard deviation of EBVs, but in this case I don't use, if you want to use standard deviation of the EBVs for standardization, it's okay. But if you can take also the standard, the square root of the genetic variance from variance components is okay. So everything commented out hash is not read by the animal. Here you can see I took the standard deviation, the square root of the genetic variance, and that is 2.58 milk. That is 2.58 kilogram of milk, one standard deviation. So if a cow in this standardization, for example, had an index of 110, that means that bull or that cow is about, has a genetic potential for 2.58 kilograms of milk above, over and above the population average. If it has 90, then it is one genetic standard deviation down than the population average. So the farmer can use, okay, anything above 100 is good animals, anything below 100 is poor animals. So I read the breeding value file. I made my genetic standard deviation. It's all just combining information. Yeah, okay. I read my reliabilities. Where do I read my reliability? So I make my standardization first here, as you can see. This is a formula I just gave you. I think the breeding value of the animal minus the mean breeding value for that group, for all those animals, divided by the genetic standard deviation times 10 plus times 10 plus 100. So this is exactly what I'm doing here. You can see. I take the animal EBVs of animal I, and the fourth column, I deduct the mean of the EBVs, I divide it by genetic standard deviation times 10 and plus 10. Once I have done that, I wrote it to a file called index standardized index out. So one thing, this gives me only standardized, that whether the bull is or the cow is above 100 or below 100, but it doesn't tell me how reliable that estimate, that breeding value. So for this case, I have to read the reliability we have estimated into this one and combine them together to make much more sense. For this one, as you can see here, I am reading now the reliability estimate. And here I am merging them together. And merging together. And then I am making indices. Now I merge, okay. I merge the index, the reliability in with the breeding value indices. Now I want to publish the indices for bulls and for cows separate. We cannot put them together because in the cows, the farmers select the best cows. In the bulls, they select the best. For that one, I read the sex information from the pedigree file. That's why I need a pedigree file here. So the cow indices I made here. And I think I have written out the file called milk cows index to a file. And I did the same for the bulls and write out milk index for the bulls. So that's all. Control KD. So if you have R, you can run like this in Linux, capital R space -F and your R script. So I enter. So it comes everything to the screen. So I want them to be the log to be written out to a file called out. I do that one. It is quick and done. So I have got different files here. Even I got a plot distribution of the, I don't know if this one works. Even say if you want to see the distribution, I can show you the distribution. It is slow, it's not coming anyway. If you do that, even say is the way to read PDF files in a Linux environment. It takes a while actually. If it, it came and gone. Can you see the plot? Hello?
Yes.
Yeah, we can see.
Yes, we can see it.
Yes, we can see.
This is a very nice estimate. You see, it is normally distributed. I don't know, my computer is somewhat slow today. Yes, this is a solution from the R run. It now plots your breeding value. This is one of your diagonals. Everything is fine. Okay. Now let us see the ranking and the. Okay, I take with Joe. Let us open the milk index for the bulls first. Here it is. We have the animal ID, the number of progeny, the number of observations, the reliability for that animal, then followed by the index. And the last one is the sex of the animal. Actually, these are bulls. It should be all M. And the highest ranking, it is also ranked from largest in terms of indices. So the 108 is the highest ranking animal in this case. So if it is 110, it is one genetic standard deviation above the population. That means he is about 2.58 kilograms over and above, has a genetic potential for that one, over and above the population. We can see cow index also. Index cows, I think it's index cows. No. I have to quickly go index cows. Here, cows are also look the animal ID, number of progeny, number of observations, reliabilities, and the indices for the cows and This is also, it is ordered from the best cows towards them. So it is clearly, for example, if the farmer takes, oh, I'll take this animal ID2, which has about 110, 114 index points. That means she is about 1 index point 1 and 1.5 index points above the population average. So this is the best bull. If I go down there, you can see very poor cows also, which are much below the average, and you can see, yeah. Okay, I think this is what I have all for this one, and as I have shown you, you can take this, for example, I would like to take only to publish, for example, you don't publish this 200 or 2000 bulls, GEBVs, or we always breeders publish the top ones. For example, if you want to just publish the top 20 animals, then head, if you want to publish the head, the first top 20 bulls, then head minus 20, then bulls 20, top 20. So let us open bulls top 20. They are here. So you can publish these ones. And if you want the cows also, you can do the same thing. So at the end of the day, using this solution, we can make them attractable or very nice readable for the farmers, like the one we did for Ethiopian farmers in Ethiopia in their national routine genetic evaluation. Can you see this one? The national Ethiopian genetic evaluation.
Yes, sir.
Yes.
Yes. We have just compiled that information, just copied and ranked the best 50 bulls or cows, the bull ID, their birth year, their breed, their herd, the progeny, their index for milk yield. If there is another trait, also we can, the reliability for that one. And we show also to the farmers whether reliability is high, when it is low. We advise also consider for selection these bulls, yes, maybe, no, and things like that. So here there is a directive. The population average is 100 and 10 index points is 1.6 kilograms above the population average. So a cow, for example, this bull is very good bull. He has about 120 index points. That means 2 index points above the population average of 100. I hope this will give you a very brief description of what all in the last couple of weeks we have done is coming down to what it is we provide to the farmers in a way that is meaningful and usable. I think this makes a little bit sense. Does it make sense?
Yeah, sure, a big sense.
Yes.
So I advise you all, I think I have provided you all, although it is not a complicated thing, in a simple, taking a single trait case, I have provided all the tools for these all activities. So if you have time to do it now, I can help you. And if you don't have time also, don't worry, go back home, sit down, relax, have a cup of coffee or tea, and try to go through it and try to understand what we have done here, how we have done it. And if you have problems, you are anytime welcome to ask me. You have all my information, I think. If there are any questions and things I can accept, and there are, you can still try to do something if you want to proceed with that one, I can help you. But there is one thing still tomorrow. You are now graduating class and just one day before graduation, but still there is 1 hour or half an hour class tomorrow. There is a thing which we have not yet covered about these test day models. Maybe I'll take that 1 hour tomorrow and to show you a bit about how you can do covariance functions and how do you calculate breeding values, daily breeding values for the animal or some test day models.
Thank you, Prof.
Question? Question?
Oh, please, yes.
Question?
Come on, please.
Yes. Is there any possibility we can do? Yeah. Is there any possibility we can do to improve the breeding values? Is there any way we can do to improve the breeding values depending on the management activities?
It's a good question. You see, to improve breeding values, one way, because it is dependent on the genetics behind. So one thing is providing a very good environment for the animal will allow also the animals to express their genetic potential. And secondly, also you have to have a very good model, a very nice model, so that is disentangles from the what we think of the genetic effects from the environmental effects. So accurate estimation of breeding values all is what is improvement. I understand the way. In most of the cases I have seen, and I have also experienced, it is possible to estimate breeding, not very good ones, which makes even the good animal looks very bad. And so you can improve this kind of situations by having a very good model, by proper correction for environmental effects. That means setting up a very good model and a very good analysis will improve your breeding values. Because for breeders now it is genomics era, and also this allows us to accurately predict the genetic merit of the animals.
Thank you.
Welcome.
I have a question.
Yes, go ahead.
Is DMU capable of running a multiple random regression model?
Yes.
Ah, okay, interesting. Because Wombat is not able to.
No, I told you, DMU, really, you guys are very, very lucky to, maybe you have been exposed to DMU, but if you have not been exposed, you can do a lot of things with DMU. I hope, unfortunately, the time is short, we cannot cover this one, but in the next course, I am sure we'll cover that one. It is possible. Tomorrow, what I'm trying to show you is how can you model a single trait random regression models or test models, covariance function.
No problem, but this one, I think I will look for you separately so that I'll try to come up with a script, but then just in case I run into any problems, I might look for you because it's a model that I need to feed for my work as well.
Yeah, please do so. The first important thing is to know how I should prepare the data for a DMU run, because we have given you everything now. You can just adapt it, prepare the data in a way that is suitable, and then try if something is not working, let me know. Send your directive file and I will help you.
Okay, thank you.
Welcome.
Hello, Dr. Neil.
Yes, Ermias.
If DM is able to run this multiple regression, does it mean that we'll be able to know the significant effects of those sorts of variation on the milk yield or on milk composition parameters?
No, in this one, I think if you are referring to Sophie's question, is we run a multiple random regression models. These are, you put different models and you feed covariance functions. But your question, I think, is referring whether if you have multiple traits and you want to test whether the fixed effects are significant or not. These are the things that you have to make just before coming to DMU, using SAS, using other programs like this. They give you a significance level and things like that. So once you made sure these facts, for example, is age of the animal affecting milk yield or not? If calving season important or birth season is important, those things you have to, because there are, especially working in our continent, there are so many things to consider, and to estimate accurately breeding values, we need to correct properly for environmental effects. And as you have clearly asked that, it is always important to know first, to understand and to make sure whatever fixed effect we feed are significant, have significant effect or not before coming to DMU or to any genetic analysis. After that, you know which effects you put in the genetic model, so you can properly correct for environmental effects, and your genetic prediction will be perfect.
All right. So now when it comes to estimation of heritability, I should allow only those effects which are significantly making a difference on the milk yield.
Yeah, yes, yes. I think it's advisable that way.
All right, yeah. Thank you.
Yeah, welcome. Has anybody able to run this R script? Or anybody trying to run? Because for you, I think it is very easy, because with Raphael, you have estimated already the breeding value solutions. You have the Solani. With Raphael, you have estimated already the reliability. You have the reliability solution somewhere. And the pedigree file you have somewhere already. I have sent it sometime. It is just combining this information into your R program and you are done. Did you have, let me ask, did you have classes on test day models? Lectures on test day models?
Are you asking if Raphael taught test day models?
Test day models.
Yeah, he mentioned.
Okay. Shortly.
Yeah.
Oh, okay. Yeah. Yeah. Okay.
Yeah, he mentioned on aspects of using fixed regressions and random regressions and the different polynomials that you can use. Yeah.
Okay. Very good. Yeah. If you have still energy tomorrow, I can show you just briefly how we can fit test day models in DMU or something.
Yeah, it will be of great interest to us, sir, because we are.
After 4 weeks, I think you are tired now.
But this thing called test day model is of a matter of importance for me because I'm dealing with it in my thesis. Yeah.
I think you can discuss also tomorrow on the comments, because when we organize the next course, what are the most important things we should focus on? So this is not the end of the things. I think this is the beginning. So many courses will be coming. So your suggestion, comment is on how to improve is of paramount. Okay, Muna is sharing her screen now. Muna is analyzing now very well DMU5. Okay, can you list? 6. Okay. Muna, could you open the log file? Can you hear me?
Hello.
Hi, Muna. Could you please open
I try to run Domo 1 and Domo 5, but I go and find the file Sol. But it's empty, zero. I don't know why. The file soul. I find
good.
it, but empty. Why?
Yeah, you have done everything right. Can you open the log one first? You remember when we run DMU? The first
DMU,
one
yeah.
When you whatever DMU run, can you hear me well? I think it's slow a little bit. Can you hear me?
Yes, I can hear you.
Yeah. Okay. Always when you run, first go through after the running DMU1, look the solutions. Is everything right? Sometimes there are error messages or something.
Okay.
If there are error messages in the first step, then the second step will not work well. So in your case, we see, can you open your directive file? DMU dir something. Yeah. No, Joe. Okay, delete Joe and ls minus space minus lrt, so we can see what files you have.
Joe?
Delete Joe. Delete Joe. Yeah. ls minus space. That's good. Good. Stop now.
This I said to you this.
Yeah. Okay.
But
I
empty.
remember. The problem is in the first step. That soul is in the second step. So open Joe log 1.
Okay.
Joe log 1. Okay, open that one. Can you slowly go down? Could you make a little bit your terminal bigger? Is it possible?
I can't. I don't.
Okay, go down. Slowly go down. You are going up.
This is the last.
This is the last.
Yes.
Go down. Okay. There is nothing below this.
Yes.
Okay. Control C. Go out. Control C. Okay. ls minus lrt. Okay. Now we know the where is your directive file? There is UNV Geo. UNVV. Very good. Go up. Control KU.
Control
KU. Or by page up, page down, you can go also. Right. Now, Control C. Control C. Okay. Page up. Very good. Everything is right. Go down. We'll check your data later on. Okay. Go down.
Okay. Here. I have to do this. This I rename it to underscore val.
Okay. Control C. I now can
underscore here.
Yeah. Do you have that file? Okay.
Yes.
Control C. Control KD. Sorry. Control KD. KD. Okay. Control C. Yeah. ls minus lrt.
Still empty.
No, not yet. Can you open this start valve, Joe?
Joe?
Yeah.
Start?
Valve. Yeah. just delete the last one. This
The last
number
row?
3. Yeah. If you go that one and control K, control Y, control Y.
This?
Okay. Yeah. Control KD. Control KD. Yeah. Or control C. Okay. LS minus LRT. One thing is now your start val file is small. It should be capital S.
Sorry?
Your start val is starting with small s. It should
Okay. I have to change here, it there.
Yeah, move MV.
Okay.
No, MV. You can move.
Okay, change the name.
Yes. Very good. Yeah. Yes. Yeah. Now go back and make it capital, that one. Very good. Enter. Okay. One thing I'm not sure is if you are reading your data, right? Okay. You can just DMU1.
See?
DMU1.
Ah, don't.
Small.
Sorry.
Yeah.
Okay.
You are right. Yeah, you can check with that one. Okay. Don't do everything. Go to the end of the line.
This one?
Go, yeah, no. Okay, with arrow key again.
With arrow?
Stop. Okay, no, back. Stop.
Yes.
Delete that.
Sorry.
Don't make enter. Yeah, delete that log 1.
Log 1?
Yeah, and that sign also. The greater sign. Okay, stop now. You can enter now. Okay, it is finished with exit code. It is done. Okay. Again, arrow key muna. It's very good. It's done. Arrow key. Yeah. Now greater sign and log 1. Yeah, very good. Now open your log 1.
Yo?
Yeah. Go down. Can't you go down? Very good. Just you are running very fast.
Sorry.
Okay. Go down slowly. Yeah, slowly go. Down. Very good. Yeah, go down. Bit faster, not very slow. Yeah. Go. Now you see your model here.
Yes.
Okay.
Yes.
Go down. Down. Let us see your data description. I think you better go with arrow key, not with that one.
Okay.
Okay. Now come out of this one. Very good. It is done very nicely.
Yeah, bro. I want to see soul inside.
Yes.
When I do zero or not or empty, still empty.
No, we are going to show you that one now. Okay.
Zero.
Open no, we have not yet run that one, the second step. It is the second step, right? DMU5.
Okay.
Space, greater sign, log 2. Yeah, enter. Ah, okay. Open log 1. Go down with arrow. Yeah. Or with a page down. Yeah, go. I want to see. Okay, go. Yeah, everything looks nice. Go. Stop. Pedigree information matrix 1. Number of animal, data in pedigree. Okay. Your pedigree file is not right.
Pedigree?
Ah,
okay.
We know. Okay, let us go out.
I will check it.
You check and
Yes,
change
I
your
will.
pedigree file.
Okay,
Everything is very nice now.
Okay,
Thank you, Prof.
Welcome.
Thank you.
Yeah.
Thank you.
Just change your pedigree file and you are there.
Okay.
Okay, guys, thank you very much for tuning in today. I hope we have seen some
Thank you, Prof.
Useful things. I will try to come for about 45 minutes tomorrow morning before your graduation to tell you a little bit about test day random regression models.
Thank you. Thank you so much.
See you tomorrow. Have a nice evening. Bye.
Thank you.
Okay,
Thank you.
bye.
Bye. Thank you, sir.
Bye.
Bye.
Bye.